Okay, welcome everybody. Today we are on session 13. And we have an opportunity to talk more about beams. The kind of two big points that will come out of what we covered today are being able to relate the radius of curvature on a beam to longitudinal strain, all right, and to relate the bending moments to bending stress. Okay, these are two kind of big deals. So just write kind of this out. Okay, this is going to be beams 3. And so our kind of two big takeaways are being able to relate the radius of curvature to longitudinal strain. Okay. So the equation that comes out here is that the longitudinal strain is going to be equal to minus y over rho. And what is this talking about? This is talking about, here's a beam, and you see it's bent. And now what we're talking about is a radius, okay, which we give as rho to this longitudinal axis, along the beam, right? So this is the, depending if you're in CDL or Hibbler or I'm talking, you'll hear terms like neutral axis, longitudinal axis, okay? And in beam bending, what we're doing is we're assuming that the length of this dotted line at the neutral axis doesn't experience any longitudinal strain. Okay, it's not changing its length. It's staying the same length. This is exaggerated. You're not going to see this much curvature in Euler beams. Okay, we're assuming small deflections. So this picture is grossly exaggerated, right? And then the y that you're seeing here, this y is very significant. This y is the distance we are away from the neutral axis. So as we, let's see, let me use this one, okay? As we look at our beams, this y, okay, is the distance away from the neutral axis. And when y is positive, we're going up, we're above the neutral axis, and y is negative, we're below. Okay? And so what is happening? We're saying that there's some lateral strain or some longitudinal strain here. Okay. We're saying that there's some type of strain the material is experiencing, and this is epsilon. Let me do it a different way, actually. So, for example, there's a lot of strain in tension there, and there's strain in compression above. What are we talking about? And this may not be the best way to signify it. Forget the math. If I take a beam, this material here, okay, this is a beam for our intents and purposes, and I apply moment to it, and I make it smiley, is the top of the beam, is it in compression or tension?
Compression.
It's in compression, right? You can kind of see like all those little material elements on the top of the beam, they're getting closer and closer to each other, right? That goes into compression. If I look at what's happening on the bottom of this beam, are those material elements, are they in compression or tension?
Tension.
And in tension, right? Okay, perfect. So what we're saying is that the distance away from the neutral axis, right, that y, that dictates how much compression or tension you're going to have. Okay? And if you are above, so if y is positive, that means you're up here. That means that your strain is negative. Okay, and that puts this, that means you're in compression on the top. If your y is below the neutral axis, then that y is negative, that makes the elongation or the longitudinal strain positive. Does that make sense? And this is saying that we have this radius of curvature, rho, okay, where it's above. This is actually a positive radius of curvature, rho, and it's above. And as you can also see, if your radius of curvature is smaller, that means you have more longitudinal strain, right? If your radius of curvature were infinite, right? If I make my radius of curvature really, really, like, let's just say I have like very little bending, right? That puts the radius of curvature somewhere like out here, right? You see how rho increases now? As the amount of bend I have is lower, right? As my curvature is lower, my radius of curvature is higher. Make sense? Okay. Let me just get rid of that. So anyway, so this is the first major takeaway from today. And there's the derivation in the notes that you can look at, okay, in the video. The second major takeaway, all right, today is that we are going to learn how to relate. So this is kind of like, this is number one. And number two is we're going to relate bending moments to what we call bending stresses. Okay, and bending stresses are normal or axial stresses, but it's a little bit different than what we've talked about here. Now, the equation that we're going to take away here is that the bending stress is equal to negative my over I, where m is a bending moment, an internal bending moment. Y, again, is the distance from the neutral axis, and I is what we call, and we kind of hinted at it actually the last time we talked about J being the polar moment of inertia. I is what we call the second moment of area. Okay, and there's a significant amount of discussion of that in the notes and in the video. The big takeaway here, okay, is just as we were talking about the top. Whoops, what just happened? What did I just do? Let's do this. Just as we were talking about the beam above, all right, above the neutral axis, going into compression with strain, you and I will see that if y is positive, that causes a negative stress, right? That's a compressive stress. And as we get further away from the neutral axis, that amount of compressive stress increases. Now, unlike what we had in the first relationship, where we're relating strain to geometry only, now the derivation that you'll see in the notes relates the stress that we have to a bending moment. So now we're actually able to relate the bending moment, which is a load on the beam, to a stress. Okay. And if we want the strain, right, since these are normal stresses, axial stresses, we can actually say, well, sigma equals E epsilon, right? And so now we can actually figure out what epsilon is as well, all right? And so go ahead, take a look at the notes and get some derivations. A little bit more, so I, all right, so this I that we have here, I is maybe a new term. This is the second moment of area. And you can kind of see if I is bigger, then the stress will be smaller. So I is related to how much a beam is going to resist, okay, resist the bending. So this is giving us an idea of how much does the beam resist bending. Okay. And it's purely based on the cross section. All right, so now what we end up doing is we say, okay, if I have a beam that you have like something like this, right? And now I look at the cross section of the beam, so I do a rotation. So I've got my beam, all right, here's my flat beam, and now I look at the profile. Okay, I'm looking at the profile of the beam. And so let's say it's some type of rectangular profile, which is kind of the most common one. And you'll see more in the notes about how to go about calculating out these second moment of areas. Okay, that'll be between questions 2 and 3 in the notes. What you'll see is a classic expression, okay, which is given by the height, the width of the beam, and like we said, I. Okay, now before I write this expression, you have some experience in life. Okay, you've walked around on supported structures, you've used tables, you've sat in chairs. Okay, what do you think? If you want to build something that resists bending, okay, right now what you see is you have, if I'm looking at a profile, I have my option to change what we'll call B, the width or the base of the beam, or the height or the thickness of the beam. Which one is going to help you resist bending more? If I increase the width of the beam, so I'm standing on the beam, right? Do I get more resistance if I increase the width this direction, or if I increase the thickness if I'm standing on it and I want it to bend less? Where do I get more bang for my buck?
The height.
The height, right? Exactly, right? The height, if I make it thicker, right, it's going to want to bend significantly less. And it turns out that this is what you see here with BH cubed over 12. All right, that's an expression that you'll see. And this comes from an integral that we can do and that we do, all right, where I is equal to y squared dA. Now y squared, that is the distance from some specified axis, all right? And you can see how we calculate those again in the notes. Now, you may think, oh, it's always with the cube, right? So the h is, the thickness is so much more important. It is more important, okay? But look, if we go to the bending stress equation, all right, that we have over here, there's actually a y that is going to be proportional to, it's going to be related to the thickness, all right, or it's how much I am away from the neutral axis, all right? So, and it turns out that these these bending stresses, all right, another important thing is the bending stresses are maximum at, let's say we have, this is our H, right, which is a different perspective, but if that's our H, the bending stresses, the sigma max for bending, it's going to be negative m over, or sorry, m, this y we replaced with h over 2. And now we have our I, right, and for rectangular beams, this means that we have sigma max is equal to negative mh over 2. This is bh cubed over 12. This means that we get that negative m, and the h's cancel. We get a negative 6m over, that's a bad, I'm sorry, I'm having trouble writing here. Negative 6m over bh squared. I want to make sure that this 6 and this b do not look the same. Okay. All right. Now my m looks crummy. Okay. This is a significant relationship. What it's saying is that the bending stress, right, is going, so yeah, if I increase the width of the beam, that helps, right? But if I increase the thickness of the beam, it helps h squared essentially. Now, do we remember something way back in session 1 when we talked about scaling relationships? Okay, actually it's not here. Let's do it this way. Way back in session 1, okay, we talked about transverse loading on beams. Look at this. The supportable load scales with h squared. The supportable load scales with b. The supportable load scales with 1 over L. Right? All the way back in session 1, we said just take this as information. If I make the beam thicker, that helps quite a bit. Okay? Look, we are now, today, after today, and you watch the videos, you will have derivations. You will have derivations that show, and we took this to, once you get this relationship, and once you get I, and then we just write this little bit of math here, that's what we're seeing here. Look, the sigma max, right? That's what we're going to be comparing to the yield strength of our materials. That's a normal stress, right? And that sigma max has got to be less than the yield strength of the material. So if, right, we want to be lower than that threshold, that yield strength, right, we got to make sure that this quantity, at least for rectangular beam, is less than that. So one way to do that is increase b. Another way to do it is increase h, and we said that goes with h squared. Another way to do it is to decrease m. Well, right, look, m, right? M is often P times L, some types of force times length. So remember what we said all the way back in session 1 is that if we decrease the length of the beam, right, that will also increase the amount of supportable load we can. Look, P times L, this is a beam, all right, that is beam bent. M is equal to PL, right? So once again, we see here, if we shorten the length of the beam, that beam will also be able to support more without breaking. Okay, so that's kind of the intro to this very important session. And one of the major things that we want to have as a lasting set of equations is, or not more than equations, but lasting set of concepts, is that we can tune the properties of a beam structure to be able to support loads, or to be able to have you know, a designated or a designed amount of strain. And where do we see beams? We see beams in so many different places. In construction, and like we're talking about, some forms of tables, okay? I mean, tables, they kind of look like plates a little bit on the top, right? In your vehicles, in your cars, there are beams in many, many different places. And there are also techniques that we use, like making I-beams, all right? So that you have a high I, and you can reduce the high I, meaning high second moment of area, but with a reduced amount of mass. Okay, so that's why we don't see. That's why you see a lot of hollow beams or a lot of I-beams, because you don't need all that mass to get all the resistance to bending that you are interested in having. Okay, so go ahead, have some fun, or watch the video or go through the notes and start working on the problems. As you see, the format of what's available on engineering content is actually a little bit better now, okay, I think. Then I haven't had a chance to make everything completely uniform, but what you'll see is now each session is broken into individual chunks, into shorter videos, and then there are questions right after those videos. Okay? And if you're interested in seeing what we're doing today, okay, you actually this is us live right now. That's there too. Okay, great. All right, go for it. Any questions up to this point? Any questions on what we're doing? All right, good. That's right. Okay, that's right. So you're going back to the other, yes.
Yeah, I just think that I can do this.
Yeah, it's so for that, if people are looking at some of the issues with applied moments and things, if you go, let's see. Okay, so some of these, I'll copy these over. Michael, this is from last semester. Because that problem, and we can talk about it, but that problem is quite intense. So I'm going to move these two, or these three. Okay, let me do it instantaneously there. Okay, let me do this. Okay, so it's available on the or it should be uploading into session 12. Okay, this semester, but it's definitely up there under. It's a little hard to find from last semester. It's under. There's a huge there's a huge kind of tab that's just office hours and notes. Okay, but it should be coming up in our current summer session. And with this problem, okay, that's on the assignment, it is tricky. Okay, it is pretty tricky, but we start off again looking at what is external equilibrium, and then looking at what's happening at the boundaries, right? Just what are the internal bending moments and what are the internal forces, shear forces, at the right and at the left, and then we can use the integral.
I think I might have found my problem.
Okay.
Is the applied force is the moment, like on the right side, is the moment caused by the applied force you're working with or against the applied moment?
They are independent external loads being applied to the beam.
So is reaction force left times L, plus or minus force applied times 3L/4, and then just plus moment applied or minus?
Okay.
For like the sum.
So when you do, it's kind of right there, right? So if I'm doing external equilibrium, right? I've got my RL and my RR, right? And I've got all these things in there, okay? Yeah, it's going to be, those FAP and MAP are both going to be close.
So what is the CD equation would be a plus or would be a plus?
So yes, because it is coming out of the board. That's correct. Okay, it's coming out of the board, right? If I'm doing equilibrium, so if I do, right, you can do it at the left or the right, or you can do it wherever you want, right? But it makes sense to do your equilibrium, right? Let me just go back here. Okay, what you're getting at, I kind of shortcutted here a little bit, right? So we can use the sum of the moments, all right, equal to 0, either in this case, right, this is doing it where I'm using this point at the left so that I don't have an RL, or this equation where I have RL, I'm doing it at the right so I don't have an RR. Am I making sense?
Yeah.
Okay, so in either case, or in both cases, I'm saying that Z is coming out toward me. So yeah, so MAP, okay, is going to be a positive,
Okay.
right? When I said, let me just write it out, right? So if let's say, it's all messy, right? But let's say that I'm doing this is external, right? And we're doing sum of the moments, and let's say that we're doing it at the left side, right? And this has got to be equal to 0. So now I'm going to have a minus F app times L/4, right? Because that goes into the board. I have a plus M app because it's positive coming out of the board, and I have a positive times L equal to 0. Does that make sense?
Yeah.
If I do it at the right side, MAP is still positive, okay, but now RL is going to be contributing a negative moment. Okay, if I do it at the right side, I have a negative RLL. I have a positive F app at 3L over 4. And I still have a positive M app. Go to 0. Okay, now, this is for external equilibrium. What's tricky, if you go back and we look at notes from session oh, sorry, it's not here. It's in 11. Okay. Remember that as you're moving along the board, as you're moving along, if you're going from the left going to the right, look at this. The plus delta M, the internal moment that you have, is in the opposite direction. So you actually have a delta M equals M app, but this M app is into the board. This is a negative moment being applied. So what you're going to have is actually a delta M equals minus M app internally as you hit this region, because this is a positive M app. This is confusing when you look at the internal one. Okay, but this is to keep all the conventions in place.
And region, but the shear force diagram, the other one doesn't do it.
Correct. But I mean, how do you put it? It can, yeah, that's right. But is the shear force affected by, what's happening at the external boundary conditions, or at the left and right? Yeah, right. So yes. Okay. Right, because we see here at the left side, right, or at the right side, that this V of 0 is equal to RL. Well, RL is dependent on M app over L. But it doesn't cause M app is not going to cause like it's not going to cause, in the V, right, you're not going to see the step change in the V. That would be, there's a step change in the moment. Yeah, so this is a pretty good tricky problem.
Should we put some moment down right now?
No, it's close. It's close-ish, but
Should speak with God.
so where is, I guess, we're missing some, okay, so, I mean, like, there needs to be some integration, right?
Yeah, all X.
Okay.
And then this is, just the both of these lines are, negative R2X, but then the jump is from
Yeah, okay, so. Yeah, and so that we also make some, suggestions for. Sorry. Right, so this, yeah, so I think here, right, so this is good, right? This is good, right? The direction of the slope though, right? This is what's a little
Positive.
And then again, right, this is also the jump needs to be down,
Okay, it's
right?
But why is this slope positive? Does it not matter that where it is on the shape graph? Is it just because wouldn't it be negative Rx?
So yeah, so it is going down, but it is actually, the way it actually has a positive value, okay? So yeah, so this is a little bit misleading. If you do the math out, right, so we put this condition here. So to be a little bit more specific and a little bit more careful, okay, and it said here, but the minus RR is actually greater than 0, right? If you do it out, if you look at the conditions, okay, the minus this, because we said that the M app over L is greater than the F app over 4, okay? So the minus RR is actually still, or this is actually still greater than 0, okay? Right, so that's why, okay, that it should be kind of like that.
So then the maximum bending moment would be at the top, obviously.
That's right. Okay.
Okay.
And then like the M app needs to be causing that jump down. Good. You're doing well. It's a tricky problem, right? It's a pretty tricky problem.
So
not, the distance from here to here is not R over L over 4, right? The distance from here to here is L over 2. Good morning. How's it going? Good.
You went over that already?
Huh?
You went over that?
We just did because there was a question about it. Yes. So actually, if you just look at the live session, this is up. If you go back 10 minutes, you'll see what we just discussed. Yes, Mike.
So I was looking at the slide.
Yeah.
That relates normal strength to max.
Yes. Yes.
And I see this diagram. The gray dashed line is the longitudinal axis, right?
Yes.
So then, how would we know if y was to this surface or to this?
So y is going to be going upward, okay, and it is the distance above. So if y is negative, then that means you're going below.
Okay.
Does that make sense? All right. So most cases, this is kind of more of an abstract drawing, but most cases the neutral axis is in the middle. All right. And so you're going, the max if you go to is y equals c over 2 plus c over 2, or y equals minus c over 2. Now, it turns out we can figure out where the neutral axis is by using what's called the first moment area, which we discussed a little bit here, but we'll also discuss later.
So if beam was like going down, would it still be?
So if the beam is going down, that means that there's actually a negative moment applied, and that rho is negative. Okay, so this is something we don't talk about. Maybe we should talk a little bit more. But when rho is considered positive when it's above, and when rho is below, it's considered negative.
No, I know.
Okay. But you're absolutely right. So what ends up happening? Usually, what happens? Okay. So yeah, we're still going to keep y being positive. Essentially, y going up is positive, y going down is negative. Right? What will change is that the bending moment will be negative or positive. So if we just go back to this equation, right? If we just go back to this equation, if the beam is bending the opposite direction, like you're saying, where it's like, so now what happens is essentially, this would be a positive bending moment. This is considered to be a negative bending moment, okay? And if we look at what's happening internally, right? Again, take a slice, look, because this M is an internal bending moment, okay? But we still associate, we go directly from, okay, this is a positive bending moment on the beam, and if you look at the cuts, they're going smiley, okay? But if I go the other direction, then M is negative. Y is still defined by the convention we're using, okay? But that means that you're gonna have Y positive with a negative bending moment is gonna give us a positive stress. So that means it's still gonna be in tension above. Like, so if I put a negative, right? So if I put a negative bending moment like this, even if I'm above the neutral axis, right? That means that, so y is positive, but m is negative. I is a positive number always, so I get my tension above, okay? And if I go over here to this equation, y is above still, all right? But if it's bending the opposite direction, then I say that rho is negative, okay? And so that then I get the positive longitudinal stress. Okay, so that's something that I didn't really say, but this is, if rho is above, then we say it's positive. If rho is negative. If rho is below, then it's negative. Okay.
Now one more thing, is C just like the radius of the beam?
C we consider to be the thickness of the beam.
Oh.
Okay, because these now can be or H, right? So we got to be careful what we're defining here, okay? Yeah, because C is often used as the radius for torsion problems, okay? But for beam, I mean, you could have a beam that's a circular cross section, and so you could use a C. We just have to be careful here, okay? Good questions, Mark.
How do we know which one's negative? Which would be negative?
Okay.
For y and all that is, like, how do we know if the answer is negative or positive?
Okay,
Is that
so
on the string?
y is negative if it's below the neutral axis or longitudinal axis.
If it's below.
If it's below, alright? If it's above, then it's positive.
So would this, is the equation negative y or is it just in
It's
this, in
negative,
this example?
so it's negative y. So if you have a y value that's above the neutral axis,
Yeah.
and your bending moment is this direction, then you're gonna have compressive strain.
Also be negative. right?
Yes, it'll be negative, right? You have a negative and a positive. Now, what Mark and I were just talking about is if your beam is bending the opposite direction, okay, then we actually will say that the rho is negative. Okay, so if rho is above the beam, then rho is positive.
Yeah.
If rho is below the beam, then it's negative.
Alright.
Okay? Now, here's something I probably should have said earlier, folks. Just listen up for a second. In reality, I usually don't think about the negative sign or the positive sign. I would just like write ny over I or whatever it is, okay? And I just think in my mind, is this in compression or tension? And then I put the positive or the minus sign on the final answer. Does that make sense? Because often yeah, you can keep track of everything, but sometimes it's just better to think about what the structure is doing and then assign the sign appropriately, or say it's compression or tension.
Thank you. So usually it's, I don't know. I'd say
Is it like, how's that longitude?
Longitudinal means it's going along the direction of the neutral axis, right? So these are long, slender beams usually, okay? So the longitudinal direction is gonna be along the beam.
So is it, but it's different here?
So the local, yes, so what we're doing is we're relating the radius of curvature to longitudinal strain, and it's also related to its position above or below the neutral axis.
Okay.
Okay?
That's a Y?
That's a Y. Okay.
So, that says here that we have to extend the cooler.
Mm-hmm.
Did I put it external parking? For this one?
Okay. For this one, right? So, this is going halfway across, right? So this would be contributing force of W. Okay, whoa, so we're jumping here. Okay, so why don't we first do balance of the forces, right? Yeah, so there are there's one force here, there's one force here, right? This, we'll call this, we can call this like R1, I guess, and R2. Okay. And so then you have one equation, right? That gives us equilibrium for the forces, correct? Okay. And then here, right, this MR, right, this external one, it's dependent on this force and this force, or this distributed force, right? So I agree, okay, with this is, yes, this, for this moment, for just the contribution of this, not MR, but just the contribution of this moment, this is correct, right? Because this is, you're right, it's W naught times L, and it's acting L or so away, so that's gonna be this, right? So what's missing is the, contribution from over here, which has to be solved, or has to be worked on looking at the forces first, right? There are two sets of equilibrium here. There's equilibrium of the forces on the beam, and there's going to be equilibrium on the moments, right? So go ahead and write out that equilibrium on the forces and the moments, right?
Like the top versus the bottom.
I don't know if it's not that, but I can handle it. Yeah, that's true. I had mine yesterday. Yeah. To be honest, like, it wasn't that bad. Yeah.
They have this, it's actually 7. I would say we use it. It's like a reusable towel. You mean a towel? No, that's not something that was like a machine. And there was like a, it was like reusable towel. So what do we do with it is you pull it a little bit, you can wipe your hands on it, and when you let go.
No, I don't know.
And then what it works, like you, well, I guess you like pop it out, clean it. So it's a towel, it's a quick, there's no carbon.
It's not bad.
So I saw that.
It's what, like,
Yeah, it's called a towel, it's just like,
yeah.
But does the machine create that actually work?
Wait, this is how it's 14.
Does it? It's the same way that's what makes it work.
No, I'm not quite sure how that system works. Does they have, it is interesting.
It is cool. I saw that. Like I just pulled on the paper towel and then like I dried my hands in it, sucked it back in, and then you pull a new one. It's a clean set.
Yeah.
It was cool.
Yeah.
So
Yeah.
2.5,
Maybe it's some place to try
Maybe
it.
a YouTube video on that.
Because it's a towel. I'm not mind blown. I was just you were complaining, so I gave you something in between. So there you go.
so yeah, let's try it.
terms of your things.
And then you have your Y, so you gotta use that
Yeah.
size ratio,
Oh, I've
negative size ratio.
And then when you pull it, and then this part is looks like a foot. That's what it does.
It's on a loop, right?
It's on
Oh
a
yeah,
loop,
you told me.
too.
Yeah, he starts at like a.
So how does it,
You know what you calculate?
does it dry when it's hanging out, or do they have like an internal loop? Does it dry?
Maybe there's an internal
Is
tape.
it-
Yeah, there's no hair dryer and a UV light and you got in towel. Okay, then it's negative. I didn't know it exists. That's probably what it was, I didn't take it apart, so I didn't know.
Because there's something about that. That's really it.
Do you make it like hard? Or
I hate every second conversation. I hate every second.
yeah.
I used to know it so.
So,
Switch to smoke both these answers.
what time do you have class?
Yeah, but it'll tell you if you got one option, right? Well, yeah, but still it's
I'm saying because I mean, if you wanna start, you have to see like what time you can start.
That's not a big deal.
12:25. Yeah, I'm class. But
It's a big part of the class, guys.
I'm sure.
sorry.
Why did everybody
Yeah.
anything? Sorry.
Um, sorry, God.
We just went
What do you
through that,
think I'm
Michael.
doing?
Wait, how did we?
Yeah, you know where the learning center is?
This it's not like anyway.
No.
You're not calling it is.
Yeah,
These
yeah.
tables, they're more like plates actually, but they have bending moments, yes. Who's talking about it? The
Yeah.
arms on your chairs.
Yeah, everything.
They're beams.
What time?
Take that.
What are the questions?
Okay.
I hate that Candace doesn't put them in order.
What? What do you mean it doesn't put them in order?
Like they're not listed in order. Sometimes.
Yeah, but what time does it work for you?
Oh yeah, and assignments, yeah, but go to the module page.
Oh, I never do that. I just go to the grades.
The module page is everything's in order.
Didn't have that.
Let me. I just look at the grades page and I go to like. any-
Oh, no,
anything
no, no,
to do
no.
yet,
Go
and
to
I
the modules page.
The modules is perfect.
Okay. Yeah, sure. Okay.
Spend a lot of time trying to get that straight.
No, I appreciate it. It does look.
Okay.
It's very good.
Yes, it's obscene.
Yeah, I'm sure.
And it's a tree.
I'm moving too. It's right here. It's just what it is. the strain be negative, it's above the neutral axis and positive below.
Okay, so we've been talking about that. If it's curved like this, like you see on the top, then yes, it will have negative strain. It will be in compression, okay? Like you see here. If y is positive, right? So y being very like that, right? If it's bent the other direction, okay, there are a couple ways to think about it. But one way to think about it is actually rho pops to the opposite to the bottom side, and rho actually becomes negative, and we keep y as positive above, right? The other way to think about it is you just flip the system upside down, right? And now your y is negative. But usually what we say is y is positive above the neutral axis. So if rho pops below, then rho becomes negative. Okay?
Wait, it doesn't say.
And like we were saying, think about, sometimes it's just easier to think, what is really happening with the beam? What does the deformation look like, and is it going to be in compression?
I just was assuming that because everything I know is going up.
It's in compression right now.
Assume.
Above, but it's in tension below. Right, the beam, a bending beam has the part, it's going to have one portion above in compression or tension and one portion below in compression or tension, right? It's going to have its opposite, right? And you know, as you go into this, one thing that you'll see, okay, as we talk about these, is you'll see people who draw, and us included, that's really bad. You'll see people who draw these beams, and they take a cut, and there's a neutral axis across, okay, and what you'll see is that, okay, the top is in compression, right, and the bottom's in tension, right? So what you'll see is that we draw these.
Oh, okay, that's what that is.
Okay, we draw these stress strain, or we draw these strain. Sorry, it could be for either, really. Okay, but you'll see that we'll sometimes draw these things, like you see here, right? And that this would be these orange things. This is like the stress, and this is going to be negative on this side, and this is positive on this side. Okay.
And can you just use, you can use the Hooke's law?
So yes, because this is axial loading, essentially localized axial normal loading. Yes, you can say that sigma is equal to E epsilon. This is truth.
But E epsilon, it'd be other way, right?
Well, I mean, I drew stresses here, but if you want to draw a local strain, you can say that it's going to be sigma over E, would be the epsilon.
But sigma over E longitude, so if you do the radius of curvature, or if you do the distance over the radius of curvature to get epsilon, do you have to use Poisson's ratio to find the other epsilon?
Well, if you're looking at strains in the and if you're looking at strains in orthogonal directions, then yes, you need to keep that in mind. But if I'm just interested in what's happening in this direction, then all I need is this, right? If I'm assuming that the stresses in the orthogonal directions are zero, then the Poisson ratio is not going to affect the way I have to do it.
Okay. Oh my god, I thought I was asking for stress in the second question. I was confused by it giving us Poisson's ratio.
So, you know, this is
So long times Poisson's ratio is for sure.
Yeah, for question one though, you use the Poisson.
I know, but I thought
Yeah, 'cause
it was asking for the stresses, so I was confused as to why it was giving us the ratio.
Yep.
I was like, what? But I agree that.
Yeah.
mechanical strength equation, it's just strain equals negative y over rho. And then, and then to make it percent, you just multiply by 100, right?
Yeah, it's not working.
Yeah. I can do it again, like 2.9 divided by 2.2 times 100. And then
Wait, are you giving E? Are you giving?
oh, I tried to like.
Okay, I don't know why. I just had to be there. I just knew I was gonna be there, Mark. That's all. Sorry that was. I don't know why.
Was it? Decimal? I don't know.
Okay, well.
Works, I guess.
Oh, yeah, yeah.
Don't know what that is.
It's cool. It's cool.
It's, what was it? That was the goal last year. DA.
Yeah, that's odd.
It's pretty easy.
No, but it's just y squared A.
Yeah, last year.
Oh, there's just an area. Went up. They really give them height, so it's like height.
So that's area.
You don't know. Wait, no, we do. Treat was. Yeah.
Stress and force. Like that.
You can cut it in half and do it long. Yeah, we do about cut it in half. It's a lot of motion.
You see.
Yeah.
So this is the area.
Yeah. It's almost hard to run.
The square to the side of the
They were doing height, length, and, alright, what's that? 1 second, so using only those.
In question 3, when you say the square, you mean like the mean?
Cross section.
You can raise it. Wait, we have. We have.
Oh, yes.
Wait, where's the stress on that? Wait, isn't this literally just this? What literally is that? Negative m times y, which is half the height over I. We're given I.
We don't need,
On the second one, the first one. I think we should.
There's no rush, but
Why
we'll get our
for the check. M is.
is there a purpose to this using?
I mean, by my rate. Okay.
Yeah.
For me, I don't wanna commit.
That's
I was optimistic, like, I can do it the same day and get it back to the school, but then I was.
It says that.
No,
It
don't
didn't
do
happen.
that, don't do that.
So I was like, ah!
Yeah, so it's
So now, I was like, I can do it,
This
even
time,
the stuff happened yesterday.
Yeah. That's okay.
And I was like, I was optimistic.
Everyone
And then I was exhausted. I
Just-
brought them home, right? Brought them home.
Y is two
But I
seven
didn't get much
two.
sleep yesterday, and the nap I was expecting to get, I didn't get yet. Cause then I was like, there was a work meeting I was anticipating, all those excuses.
this kind of being that we're looking at as something that we
Ah.
session.
Yes. So there's some interesting points here, right? So,
With compound fraction, we can make that a solution.
okay, so one, this is an old exam problem, or a modified exam problem, right? So if you're interested,
There's two, right?
but, okay, so there's some discussion on this problem, how you go about it. Now, there are a couple ways to take a look at what the bending stress is in this region, okay? One is to move from the left and go to the right and account for these reaction moments and do the whole thing out, which is what you'll see if you look at exam 2 from 2015. Another approach, okay, is to take a slice and cover up the left, okay? So if we take a slice and we cover up the left here, right, and then we're looking at that, then we only have to account for this, you know, what's happening to the right. And you need to do careful equilibrium there, okay, but that's potentially an easier way to attack the problem, okay? But,
Would there be would there be an internal force in the x direction? If you cut there?
no, there's no axial
P to NPA.
force in this system, alright?
Apart from the moments or
Yeah, you had to account for what's happening with this distributed load, right? That's happening there. And there's no, at this right end, there's no applied bending moment, right? There's no external bending moment, and there's no applied external normal transverse force, okay? So, starting from this right side and moving left is simpler, but there needs to be some math done appropriately.
when you get an equation for the bending moment, how do you then find the growth?
Okay, so in this case, yeah, okay, Matt, you shook your head. Why are you shaking your
Oh
head?
no, I just shivered.
Oh, you shiver? Okay.
No, I'm-
All right. So, you don't always need rho, right? That's part of the bending formula, right? That we spent some time deriving here, or the flexure formula, sorry. All right, sigma is equal to negative my over I. So what's important here, if we're figuring out the bending stress, right, sigma, is we need to figure out what the internal bending moment is. Okay.
And would m here be a function of x? Or no?
Yes, it's definitely a function of the distance along the beam.
So do you like integrate or something with the flexure formula? Or
So you need to figure out what the local bending moment is, and that may require some integration. You have different way, or you could do it with equilibrium.
okay, I get it. Okay, I think I get it. Okay.
And if you want to take a look, there's actually, we discussed this, since you brought it up. No, where is it? Actually, in session 14, I'll copy these in, okay? But this was a topic of discussion that we had back last semester. So if you look at the notes, I guess this kind of does it for you. Actually. But take a look. So a little bit of, so you can click on this if you like. Do you use Notability or do you use something else?
What?
What do you, for your, or is that a Surface? Are you using,
Yeah, Surface.
you use a Surface? Are you using OneNote then?
Yeah, one.
Yeah, that's, I mean, that's what I use too. I don't know what else is better for a Surface, if
I
there's
haven't
anything.
tried. I mean, I used to try this one.
Yeah.
It's comfortable.
Yeah, it works. It works. I mean, I use it too. It works.
I run out of space. I have to like buy storage.
What's that?
I run out of space. I have to buy more storage.
Oh, really? How many gigabytes do you have?
Originally it was 5, but now I have 100.
For wait,
For the storage, like in the Microsoft
on the cloud?
in the cloud. 'Cause
Oh. Yeah, you know, you can store the notebooks locally though, can't you, on your computer?
I think
Yeah.
I like it in the cloud because I have multiple
Yeah.
devices.
So, oh yeah. So that's fine. Yeah, yeah. So a long time ago, there was a thing where I could get 30 gigabytes from Microsoft. Like I just clicked on this thing that got me 30 gigabytes, and so now I have 30 gigabytes and I don't have to pay for it. And that's like that's a sweet spot, right? Because it's
Yeah.
like just the right amount. But I use Google. With Scarlet Mail, or we have infinite space in Google Drive. Yeah. So if you use a Google Drive, you have like infinite space. I don't know what happens after you're a student, but at least while you're a student, take advantage of it. So I use Scarlet Mail Drive, even though it doesn't work as that's what I do.
I'll try to use that because
Yeah.
I'm paying for that.
And then but I can see that being a pain.
That Surface?
This is a Surface, yes.
Which one is the 7 or 8?
This is actually an 8.
8.
Yeah, this is an 8. So I bought it from Best Buy. Oops, am I supposed to say? Anyway, I bought it as an open. It was one of their display models, so I got it very discounted, but only had 128 gigabytes of hard drive. So then I bought more. I bought another SSD, and I installed that, and now it has 1 gigabyte or 1 terabyte of storage. So it should be. I hope it's good for a while. But yeah, I have a Surface 4 that I still use at home. I had a Surface. I had like the original Surface as well. So yeah,
They're pretty good.
yeah, they are.
Actually, regret getting the ads because it's like very limited with the SQ1 chip. Like some of the apps doesn't run it. So
Okay. So yours is an ARM. It's not.
yeah, it's an ARM.
It's an ARM. It's not the. Yeah, I looked at doing that and I was like, I don't think I can risk it.
Yeah,
I can't risk it. Yeah.
Don't work.
Yeah. So So I got the. But getting one off of Best Buy, like an open box, that was to save significant amount of cost. Yeah. But I will say that I've had trouble with this guy. It has trouble restarting. So what I've found is if I leave it in sleep, as long as I don't shut it off completely, it boots up fine.
Oh,
And so I had enabled hibernate. I stopped doing that. So as long as I don't hibernate and as long as I don't shut it off, so of course you can't leave it in sleep forever,
Yeah.
right? And when it has updates, it has to restart and all that stuff. But yeah, sleep it's very good. It's very stable.
okay.
Yeah, sleep. But on the other, I don't know what they did. But powering on and powering off, I can't understand it.
Have you ever had any trouble with the keyboard, like not working?
I haven't yet. I used to. So this is the first time I have a cover. The other ones I just use a separate Bluetooth keyboard.
Oh, okay.
So I I have carpal tunnel, acts up sometimes. So I found that there's a certain keyboard. Actually, they're ThinkPad keyboards that are very nice on my fingers or on my wrists, and so I use those. And most of the time I'm Bluetoothing, but I do like the cover, when I'm traveling or if I'm even at home. It's just very convenient.
Yeah. 'Cause mine, for some reason, like I don't know if it's like these like sensors here or the color that's stopped because it stopped working.
Oh, okay. That's a
So
pain.
weird.
I'm
I
sorry.
hope it's just the keyboard that not the laptop.
I don't know.
Okay, so that's annoying. I've never. That's interesting. You connect it that way. You
Yeah.
connect it backwards.
No, well, when I flip it, yeah, because I don't like having.
Yeah. Got it. Oh, that's
When
clever.
When I'm using, I'm just putting.
That you just taught me something.
Yeah.
I haven't tried that. I mean, I guess you can just detach it completely, but yeah, you can turn it.
Oh, you can have the attach it.
Huh?
Like that one is that one magnetic too? Or?
It is magnetic as well. Yeah, it's the same.
It makes sense.
I think it's the same. I don't know. That's cute. I haven't done that before. That's cute.
I didn't know. I just saw another guy doing it. I was like, oh, I'm getting this like dirty for.
Right. So like, yeah, that's cute. That's cute. That's cute. Okay, good. We just had our circus geek out session. Alright. What's out?
Is this question 3 supposed to be negative?
Okay, what do you mean by that?
Like, is the answer, is the stress supposed to be negative? So I wouldn't think so, but that, the formula, negative numbers.
To be honest, I don't remember. Okay, but the moment. Where are we asking? This I'm asking. Okay, 3. It's above the neutral axis,
Okay.
so that it should be in tension.
Which is
Positive. Yes. That's what you said. Yes.
He agreed, he didn't say it was wrong. No, right there, I'm sorry.
oh, you got figured it out.
You got it later, so.
Yeah, what God negative, that we can't say.
Yeah, because your y is positive and your m is going to be your internal m is going to be negative.
Oh, where did I go?
I don't know. Well, I mean, this is going to need to be negative, right? So let's just back out, right? It's going to be negative my over I, right? And y is positive, so m needs to be positive. Or I mean, n needs to be negative, right? In order for this, like, because this is bending, right? This direction.
Yeah, I have it negative.
Well, you didn't. It's not drawn.
Okay, it's a pure wrong.
Yeah. But
But is that the second it's going?
so this I wouldn't do it this way. No, this I don't necessarily. So you're saying where's R? I don't see the picture.
Here it's the reaction force.
No. So that's not how you want to do it. All right. What you want to do immediately is you want to go from the left because this reaction force doesn't take into account what's happening on this side of it.
So should this graph look?
So what you want to do is you just want to take a slice, right? You want to just draw all this thing and you have a distributed load, and then you want to start from the right end. There's no R here. There's no M here. Okay, so you can figure out exactly what the internal V is and exactly what the internal M is just from that.
Oh, okay.
All right. So if you look,
So take a cut moving in from the right hand side.
yeah, that's right.
Okay.
That's correct.
And then do this stuff.
That's right.
Okay.
That's right. And I guess you can just flash. There's a there's a little derivation of it actually here on the OneNote now. So after you've worked on it a little bit, if you go to session 13 for our semester or for our summer course, you can find it there too. No, that's next session.
So that's next session?
That's next section. But the stuff above it is completely relevant to this
Yeah.
session. Yeah, don't start doing, that's the transfer shear. We're gonna do that we're gonna do that tomorrow.
Oh.
We're gonna do transfer shear stress
Am I
tomorrow.
drawing the shear force diagram starting from the right too?
Yeah.
I believe
So it goes that one.
I might believe it's actually, because then you release the moment, and then moment
So-
goes to that.
There's gonna be a balance, right? That with, for, you know, if you're cutting, right, you're showing, you're gonna have this going up, that's correct, right? And that's, yes, so that's gonna be
To
balancing more and more, right? As I move more and more, right, I've got
do the stop back.
that W, right? times that
I never
X.
showed you the first stage.
So yes, it's gonna be going up.
So my shear graph is like this.
Your shear graph was good. Your shear,
Oh,
this
so
is,
yeah. So
your shear graph is good,
so
right?
it goes like that.
Yeah, the drawing is, yeah.
So well,
So at the right, it's going to be 0, and then, yes, it's going up with, X and W naught.
you didn't print this?
Okay. Good luck, guys. Folks. Peoples. I think that wraps us up for today. See you tomorrow.